Hi, I am Kishan Jeeveswaran. I will be presenting our ICML paper, Bio-Inspired Replay in Vision Transformers for Continual Learning. This is a joint work with Prashant Bhatt, Bharam Zunus, and Ilahi Arani. Real-world computational systems face multiple non-stationary tasks and data streams. Like biological organisms, these systems should continually learn to adapt to new scenarios. However, deep neural networks are designed for stationary data, making continual learning challenging. CL violates this assumption, causing catastrophic forgetting of old tasks. In contrast, the human brain learns and remembers experiences without catastrophic forgetting. Thus, we hypothesize that emulating the learning mechanisms in the brain can help effective continual learning. The versatility of the brain can be attributed to the rehearsal of abstract experiences through multiple memory systems and constructive use of noise at various levels. As is the case in brain, we hypothesize that noise can be a valuable tool in improving generalization in representation rehearsal in vision transformers. The baseline approach employs episodic memory replay by storing raw images which raise privacy, security, and memory footprint concerns. In addition, it employs snapshot of the working model as semantic memory. However, these are not consistent with the learning mechanisms in the brain, wherein it replays abstract representations and involves a dual memory system to consolidate the knowledge across tasks. In order to better reflect the mechanisms in the brain, we modify the image replay and snapshot semantic memory approach of the baseline. Specifically, we store representations after the first layer of the transformer architecture instead of raw images. This alleviates privacy concerns and makes the approach more memory and compute efficient. Instead of taking a snapshot of the working model at task boundaries, we employ exponential moving average of the working model as semantic memory to better consolidate the learned information across tasks. Though, though storing representations in the episodic memory alleviates privacy concerns, it lacks diversity, resulting in overfitting on the stored samples during replay. Emulating how human brain exploits noise to facilitate adaptation in dynamic environments, we employ various controllable noises at different stages of the architecture. Analogous to replay of novel samples in the brain, we linearly interpolate representations belonging to different classes or tasks, which brings diversity for the experience rehearsal, thereby reducing overfitting. Self-attention forms the core component of the vision transformers, and we inject a novel noise into the scaled dot product attention map at each self-attention module, while replaying representations of old task samples. By stochastically injecting noise into self-attention, we discourage BiRT from attending to sample-specific features, thereby potentially mitigating overfitting. We introduce a synthetic label noise wherein a small percentage of the samples are reassigned a random class. To mimic trial-to-trial variability in the brain, we inject noise into the logits of the semantic memory before applying consistency loss. The final learning objective of BiRT can be categorized into two components, namely cross-entropy loss and consistency loss, with respect to the semantic memory for current and past tasks. Thus, the working model is learned on continuous streams of tasks using these two loss functions, and the semantic memory gradually aggregates the weights of the working model through EMA updates. BiRT shows consistent performance improvement over the baseline across all metrics and datasets, even under low buffer regimes like buffer size 500. The controllable noises improve diversity in stored representations, for example in TinyImageNet, where samples per class is really low, and help BiRT gain better generalization and lower forgetting. Analyzing the performance under adversarial attacks and natural corruption sheds some light on their reliability in safety-critical applications. It can be seen that BiRT is robust to adversarial attacks as well as corrupted data, and learning with noise results in improved robustness. As learning progresses through a sequence of tasks, BiRT retains the attention to important regions in the image better than the baseline approach. We conclude that the attention noise helps focus on class-wide features rather than sample-specific features, thereby reducing forgetting. Here we study the improvements brought about by different components in BiRT on C500 dataset. We can see that the exponential moving average improved the performance and the proposed controllable noises play a constructive role. In conclusion, we proposed BiRT, a novel non-veridical rehearsal-based continual learning approach with a semantic memory and controllable noises at different stages of the network. BiRT outperforms other approaches in low buffer regimes while being efficient and robust. We hope that our analysis would encourage researchers to study more brain-inspired approaches in continual learning. Thank you.